Bitte, hast du es.
Okay, our next speaker, Paul Tavolato, is Academic Director of the Master Program Information Security and head of several research projects at the St. Pölten University of Applied Sciences. And today Paul is going to speak about the detection of man-in-the-middle attacks on industrial control systems.
Okay, thank you. Well, let's make it, I think if someone has noticed that, I think the program is called Man-in-the-Middle Attacks on cyber-physical systems. But essentially in this context I would say that industrial control system is just one special version of a cyber-physical system, and therefore it doesn't make too much a difference. So first let's see what do we mean by industrial control system. We mean just a system which contains on the one side the real physical world, so cyber-physical system. So we have real sensors and actors which are controlled by PLCs, RTUs, and somehow connected to each other. This system then is supervised by the SCADA system or supervision network system, and usually in a company you also have an office network. Years ago this was not a problem because these were clearly separated areas which did not have any connection to each other, which has changed now. So all these systems are interconnected, and therefore of course vulnerabilities, which we know very well from this area, can now just progress to the other parts of the control system. Yeah. So this is just now the real problem, and we have some other problems with industrial control systems, which we maybe make it a little bit different from normal IT systems. So we have, for example, let's say just somewhere update risks. So industrial control systems usually are well 7/24 systems. So they have to run 7 days, 24 hours each day, and we cannot just shut them down for 4 hours to make a security update or anything like that. It's just not possible, yeah, or too expensive if it would say the other one. The other thing is, of course, industrial control systems, usually the software coming along with industrial control systems, lives as long as the machine they control. So life cycles of machines are about 10, 50, up to 20 years. So if you go, we have 2016. So if you go 20 years back, we come 1996. So probably in control systems, you sometimes have Windows 89 systems running, or Windows XP maybe. Yeah? So for these systems, you do not even have security updates. They are no longer supported. So there are no security updates, though we know a lot of vulnerabilities in there, so it doesn't even make sense. So you have outdated systems. On the other side, you also have special system needs. So, you know, sometimes industrial control systems are operating in an environment where security updates is not as easy to be done than anywhere else. Yeah? For example, just think of an oil platform out on the sea. So in order, you cannot just say, okay, this is our specialist for Windows Server updates, we will send him there. No, you can only send him there if he has undergone a special training so that he is allowed to go on the platform. And I think there's not so many people who have both properties or abilities. And on the other side, you have a lot of proprietary protocols, which heavily depend on the application environment you're in. Some application environments, you just have a lot of different protocols, not standardized. Every company providing it does its own idea. On the other side, you might have special areas where you have specially crafted protocols which are used just in this one area. Yeah? So it makes it really complicated to do that. So which means conventional IT security measures, all these kinds of perimeter security, so do not work here. So that was the starting point of the project I'm talking about here. And the idea of the project here is to do a behavioral analysis. If we cannot prevent attacks, at least then we should be able to detect attacks as soon as possible. Yeah? If you go to the last statistics which were published about 2015, that the average time which elapses between an infection of a system and the detection of the infection by the system administration is about 200 days. Yeah? So in 200 days you can do a lot of mischief. And the longer it lasts that you detect an infection or a compromise of the system, the more expensive it's going to be. So the idea is here we observe the behavior of a clean industrial control system. We define patterns of such normal behavior. We do this by using machine learning algorithms, and then we execute attacks against the system and compare the behavior. So the idea is just to find a model of normal behavior of the system in a way, in an intelligent way, so that it makes possible to find to detect real attacks when comparing this model of normal behavior with the real behavior of a system. So to start with, for this talk, we started with a simple system. So the question is, how do you start? You know, industrial control system or cyber-physical system is a huge area. So we thought in order to try it out, we just built one, a small one. Just a nice little setup, a testing system, and we try out what we can find there, and then we can do this. This talk is going to be a little bit restricted to Man-in-the-Middle attacks. Nevertheless, we have already done other attacks, and I will present some results on the other attacks too. So, what did we do? You see, this is a good excuse. This project is the only thing why we do this project. This is a good excuse to play Lego. We really love that. The idea here is that, you know, we have a small conveyor belt here, and you can start the system. This conveyor belt has about 3 or 4 optical sensors, so to find out whether the pieces are coming along or not. In the middle here, this is a simulation of a heating chamber. So when the products come here, they are stopped here, they are heated up to 60 degrees centigrade, and when temperature is 60 degrees, then it goes on to the next thing. The important thing, what you can see here, is that this is not just a Lego play stuff, but we have the control of the system is real control units. This is a Siemens Semantic PLC. Is here on the left side. On the right side is also a Siemens human machine interface for the operator to control the system. So in order to make it realistic, we use real hardware from real control systems. Shall I give you an idea here? This is just a short video, so you see how these things work. We start the system here. This is the start button then, and that's the first thing that goes to the heating chamber. It's going to be heated. The next, if the temperature is reached, which is about 10 seconds to go, and then it comes on, and then the next one, and so on. I think it's quite nice to see that yeah, it's stopped now. So just to give you an idea of it's a really simple system. So this is a bit the description of the scenario here. So we have this Siemens PLC and the Siemens HMI system, and they are connected over a switch, of course. And this switch is also connected to, on one side, to a microcontroller and to a firewall, which leads it then outside of the whole system. And we have the engineering PC, which is just the TIA portal used for programming PLCs. So this is just for the developer, the interface here. And the next thing, what we were doing data acquisition. So we try to get near real-time data from the PLC, and we log that. Yeah. So we log all the data that comes along with the PLC. So all the sensor data which comes to the PLC, all the actor data which goes from the PLC to the actors, so on, off of the motor of the conveyor belt system, the temperature, sensor data from the temperature, and so on. We implemented, in order to do that, we have a Modbus TCP server implemented on the PLC. So Modbus is quite a very often used protocol for these systems, and we log all sensor and actuator data. So this is quite normal way of doing that. Now come in the first two intelligent things you have to devise here. The first one is you have to define a life cycle. That sounds rather easy, but it's not at all in practice. So a life cycle means, so when do you think the process of the production repeats? Yeah? What is a cycle of repetition which makes sense? Of course, the more complex the system is, the more complex is the question how to define that. So what we really did, we defined the process life cycle as being 10 pieces being processed on the system. Yeah? So altogether this comes up to 2 minutes and 20 seconds. And within this cycle of 2 minutes and 20 seconds, we get 2,800 log entries. Yeah? So 2,800 log entries where just think like the optical sensor gives us a yes or no, whether something is passing by or not. The temperature sensor gives us the actual temperature, and the actor data like switching on the belt, switching off the belt, switching on the heating, switching off the heating. So all these real simple data is collected and gives you a lot of, interestingly enough, a lot of data to be found here. And then the second, so I said that the first intelligent question is what is the cycle time you use to get into it. And the second question is then which features do you use? Yeah? You have a lot of features. You have all these sensors, you have these actors data, you can do a lot of accumulated data about the sensor data and actor data. So in order to reduce the dimensionality of this system, you have to extract just some features out of that. Yeah? And of course, it's not random what features to extract. It makes a big difference in terms of the overall goal to detect the anomalies, what features to detect. So the idea was then, after some experiments, we reduced it to 32 features, which we were collecting. This is an example here of 4 features from the temperature sensor. Yeah, the 4 features from temperature sensors we extracted were the minimum temperature. You see, this is 20 degrees. This is the minimum temperature. The maximum temperature, which is 60 degrees, that's the temperature set but programmed to be heated. And then we have the temperature standard deviation and the temperature average over the 2 minute and 20 second cycle. Yeah? So over the 2 minute and 20 second cycle, you get a lot of temperature values, essentially every 10 milliseconds or something like that. And then you just calculate the average and you calculate the standard deviation. So this is just an example for it. Yeah? We have other examples then for, you might think it's complicated to say, well, does it make sense? Let's say the actor data, like just switching on or switching off the data. It's just Boolean, yeah? So 1 or 0 coming along. On the other side, even there, things like average does make some theoretical point of view. I think it's quite easy. This is any point in time is a point in a 32-dimensional space. And then what you can do is you find out how can you measure distances within this space and what kind of clustering could you use in order to define sort of the cloud within this 32-dimensional space of your measurements. And then we made a lot of experiments on that with different measures for distances, with different algorithms for doing the clustering, and essentially for the result of this, you see there's there's just a table where you get different distances. Euclidean distance, that's what you usually know as geometrical distance, what you've learned in school, but there are kernel Euclidean distance, Bregman Divergence. So according to just our experiments, we found out that Bregman Divergence is the best suited distance measurement. And the best algorithm was a KNN algorithm with k equal to 3. So k nearest neighbors and 3 nearest neighbors algorithm to find out. And then you get these are the different values that come along. You see they're somehow between 0.01 and 0.05. I think yes, it's the largest things of that. If you can calculate then a mean value, you can calculate a mean value out of that, which is something like 0.028. And then you can say, okay, and now we have just a threshold up and down these values and say everything which is within this threshold is defined to be within this cloud of points. And if it's defined within this cloud of points, it's normal behavior. And if it's too far away from that, it's so usually what we did, we took 3 times the maximum distance within the normal behavior to be used as a threshold. So the threshold was about 0.15 plus minus to go from this 0.0 to 28, which was the mean value of these things. And if you have that, then you can calculate an outlier. Yeah, you can put this together and say, okay, what's my outlier value? My outlier value is if it's more than the threshold away from the mean value. Yeah? The mean value is 0.028, and we add this plus 0.15, and if it's more than that, then it's an anomaly. Then it's not normal behavior. Yeah? This 0.115 is just, an educated guess. So again, some experiments to see what it is, but 3 times the maximum distance is at least a rather good value in the sense of that you say, okay, even if it deviates more or less, or if it deviates relatively much, say about 0.115. So it can deviate a lot and still be called normal behavior. This is important because this threshold gives you a slight idea of how many false positives you get. If the threshold is too small, you will get a lot of false positives. You will get some alarms or anomalies which are not really anomalies. They just deviate a little bit from the valid behavior. Okay, so that we got that now. We have this value and say this is our normal behavior, and the normal behavior is more or less defined by this outlier. And the next step we did, then we made man-in-the-middle attacks on this system. Yeah? So here is just a little bit the idea. You have the PLC on the network, the engineering workspace, and the Modbus logger, which logs the data from the HMI and the PLC. And then we just got into here as an attacker and did a man-in-the-middle attack on here. We did that just by using EtherCAP and RP poisoning, so just standard methods of doing that. Yeah, of course, first step was just a man-in-the-middle attack, just deviating the data stream, just reading the data and sending it on its way again. So no changing of data, nothing, just reading it, yeah, just listening to the data. And then you can come our results for this. Did this, of course, several times. And they were now compared to the threshold. Now you can see the average valid behavior was this 0.028 for our outlier value, and the man-in-the-middle attacks gave values like this. So these are, of course, far beyond 0.15 even. Yeah? So they really give a good, considerable, the differences of considerable extent, so that the detection of the attack is beyond that. So it's really quite clear to do that. We were really a little bit surprised by that kind of clear difference we got here, because we were not doing nothing, we're just listening to what's on the network. It's not really doing any really bad things. It's just listening. When just giving you an idea, it would be a little bit complicated or a long time. explain that. The idea is mainly that this has to do with time. If you do a man-in-the-middle attack with RP poison, you just deviate the data stream, and this gives a little bit of delay to the data stream. And this delay can have, if the features are selected accordingly, can have this big an influence on it. Yeah. So it's really it has a lot to do with time, and that's the only explanation you can have for that. You know, it's just by saying that the data, the log data, comes without a timestamp. Yeah. So the timestamp is done by the logging. Nevertheless, you see you have a delay of that, and this delay then turns out to have an effect in the mathematical sense on the deviations, on the standard deviations, and on the mean values. So this was quite clear here. So just to see, we did not stop at simple man-in-the-middle attacks. These were just other kind of attacks we tried out on the same system. So first line gives you the normal behavior. The man-in-the-middle attack is this one we already talked about. Then we made a DOS attack on the PLC. You can see this is clearly a big deviation, which was expected in that way. Interesting is that a DOS attack on the HMI did not show big influence on that, which is a little bit sad, of course. We are still working on that. Maybe some other features can come in and to improve that. Usually you would say, okay, who would attack the human-machine interface? Yeah, does not make any sense. In reality, in many situations, attacks on the human-machine interface, especially DOS attacks on the human-machine interface, go along with normal attacks. Because what's the goal of that is just to show the operator that nothing's happening. Yeah, the human-machine interface is just overwhelmed and still shows you the values from 10 minutes ago. So the operator would not notice that something's going on. Then of course we had replay attacks, reprogramming the heat rate, reprogramming the maximum temperature, so really things what an attacker would do if he's in this system. We had then two things, just Modbus read I/O values. This was not clearly defined, so we could not detect an anomaly here. And on the other side, if you write that, of course, then you have better results on that. So just this is the up-to-date situation of our experiments. So what we still, of course, doing, trying to rearrange the features and going to find maybe have even these two things getting better into a thing. On the other side, I would say we're quite satisfied with that result so far. Yeah? Of course, you have to. This approach has so far it has two restrictions. It's carried out in a lab environment, yeah. So there is nothing else happening on the network. So we have rather clear situations. Good question how that looks in real practice. And the scenario is rather simple, of course, with a limited number of sensors and actors. This has mainly to do with performance problems in calculating the outlier values. On the other side, we could say we used up-to-date hardware and firmware. Yeah, and I guess it's less, not more than 10% of the industrial control system out there do that. Yeah, really updated firmware of the PLC. And the last updates, last 1-2 updates of the PLC were mainly security updates. So the execution of attacks on the real-life system is much easier than in our system. And to end up here, conclusions, so man-in-the-middle attacks can be detected by looking at anomalies. Necessary are patterns of normal behavior. These patterns can be derived using machine learning, and the results are clear enough to make the process a candidate for use in real scenarios. And what we are working on, I've already told you, we're working on other types of attacks, which we are right in the middle of it, showing you some of them. The next step is we try to use data not from our simple system, but from real industrial control systems. So I think we have now finally agreed on a non-disclosure agreement with the company, and we will get logged data from real systems. So to see whether this approach is working with real systems, and then try to apply it. Of course, it's not as easy because you cannot do the attacks on the real system. So you have to simulate the attacks on the system and see how. But this is the main thing. Some other things we have in mind, of course, is to make feature extraction a little bit more automized. But that's what I wanted to tell you. I want to thank myself, Olga Eigner, and Philipp Kreimel, who did the main part of the work. And I'm open to any questions.
Okay, we have time for maybe one short question. There is one. Yeah.
So you said you used machine learning algorithms to say define anomalies and so forth. So the question for me is, if you know this as an attacker, if you use this kind of algorithms, couldn't you try to go underneath these kind of limits you set, the thresholds?
If you have real attacks, of course, you could adapt the threshold. I think that's what you mean. Yeah, we have a rather big threshold, and the question is what the real threshold is always a little bit of trade-off between the number of false positives and the sensitivity of the system. So at the moment we are rather satisfied with that threshold, but of course when going to real data, then
Okay, thanks again to Paul.